Hello dear students, welcome to Pen and Paper Chemistry on YouTube.
Hello dear students, welcome to part 5 of the topic thermodynamics. Now we are breaking it up into small parts so that it's easier for you to understand. We're taking up first the zeroth law of thermodynamics. Zeroth law, as the name indicates, stands for zero. Why is it the zero law? Because the first law, second law, third law of thermodynamics were already formulated, and when this was determined, but it was felt that this has the most important relevance compared to the first, second, and third, and that is why it was given the first place. And in order to avoid confusion about renaming, we called it the zeroth law of thermodynamics. It's nothing but the law of parallel lines. Simply, if you have a line parallel to the second line, line L parallel to line M, this in turn is parallel to line N. You have L and N are parallel to each other. Simple. So, zeroth law of thermodynamics, you have three systems, A, B, C. A is in thermal equilibrium with B. Thermal equilibrium. Now let us understand that first. Let us suppose I have not connected A and B over here. Sorry, C is not connected. If let us suppose A is at a temperature of 35 degrees Celsius and B is at a temperature of 25 degrees Celsius, you connect them by a conducting wire through which only energy exchange can take place, only exchange can take place. You will find that both of these come down to a temperature T degrees Celsius, which is intermediate between 35 and 25. Heat has flowed from body A to body B and vice versa till they reach a temperature where they are at the same temperature with each other. If similarly A is in thermal equilibrium with a body C, so that means A and C are also in thermal equilibrium, means A and C are also connected and they are at a temperature T. If B and C are also connected with each other, they will also be in thermal equilibrium with each other. In other words, if body A is in thermal equilibrium with two other bodies, then those two bodies are also in thermal equilibrium with one another. In other words, the heat continues to flow, but the temperature now remains constant. Coming to the next, first law of thermodynamics. First law of thermodynamics. Now, without making too much gung-ho about it, it is nothing but the law which you have been learning from your class 6 level. The law of conservation of energy. You can't create energy, you can't destroy energy, it simply changes its form. You switch on a light bulb, the electrical energy changes to heat energy, which in turn gives you the light. Simple. An electric kettle, the electrical energy converts itself to heat energy of the heating coil, which in turn heats the water, so that gets converted into the heat energy of the water. Toaster, your gas burner. Gas burner is nothing where you are burning fuel in order to get heat and light. So chemical energy here is getting converted into heat and light. As simple as that. So first law of thermodynamics is nothing but the law of conservation of energy. You cannot create energy, you cannot destroy energy. Energy will only change its form. Only thing is, we will go a step ahead because you are no longer in class 6. You are going on to higher studies. We shall now include our thermodynamic terms which we have introduced in the earlier lessons. We've introduced internal energy, work, heat. You know that work done on the system is positive, by the system is negative. Heat added to the system is positive, heat removed from the system is negative, simply. Now, when you do certain amount of work on the system, its internal energy will increase. When you add Q amount of heat to the system, again its internal energy will increase. And we know very well that internal energy is a state function, it's not a path function. So if we have internal energy, the initial internal energy denoted by U1 and the final internal energy denoted by U2. The difference of the two is given as U2 minus U1. That is delta U, the change in internal energy. You have done W amount of work on the system. You have added Q amount of heat to the system. Hence, the total change in internal energy is given by W plus Q. This is the mathematical representation of the first law of thermodynamics. Again, from examination point of view, if you are asked to represent the first law of thermodynamics mathematically, you say delta U is equals to W plus Q, where delta U is change in internal energy, W is the work done on the system, Q is the heat added to the system. How does this representation change? Why am I stressing on 2? If on the other hand you want to write that Q is the amount of heat removed from the system, then delta U becomes W minus Q. Or if you say that it is the work of expansion, expansion means the work is being done by the system, the gas is expanding, then in that case W takes a negative sign and you have delta is equals to Q minus W. So that is why when you are representing it mathematically, you have to clearly state whether W is the work done on or by the system, Q is the heat added to the system or removed from the system. As a standard, we will follow this equation. But when doing the numericals, we shall take the sign into consideration. I've taken a very simple example, although you'll say that it is quite irrelevant to take this example, but then it makes the concept very clear where you have to put the sign. Question is, calculate the change in internal energy if a system absorbs 40 joules of heat and does 10 joules of work. If you notice over here, does 10 joule of work, that means work is being done by the system. Absorbs means heat is being added to the system. In other words, our Q takes a positive sign, whereas W takes a negative sign. How will I proceed in numericals? Like this. I'll write W as W. I'll not write W as minus W. So W here is minus 10 joules. We will just put the sign in the numerical value. That is the numbers. Q, that is the amount of heat absorbed. Because it's the heat absorbed, so we have plus 40 joule. Now we will put these values in our standard equation that we have written over here. Delta is equals to W plus Q or Q plus W. So delta is, Q is 40 joules plus minus 10. So plus minus minus. So 40 minus 10 gives me 30 joules. In other words, there is an increase of 30 joules of internal energy of the system, since we are getting a positive value over here indicating that there is an increase in internal energy. It would be in your best interest to try as many numericals as you can based on the first law of thermodynamics and get ready for an expanded form and more in-depth study of the same law. We shall be relating our further equations with respect to the mathematical form of the first law of thermodynamics. So request you to study it before you go on to part 6. Thank you for watching. Have a good day.
The only mission of this channel is to make learning chemistry easy and fun for all you students. With the help of the periodic table, the flowcharts, the graphs, diagrams, dealing with numericals, how to deal with numericals, and This can only happen when you keep a pen and notebook ready so that you can also take down notes for offline reference. There is no subscription to join the channel, there is no payment at all. Only request is to help spread a word about the channel by sharing it with friends, classmates, juniors, seniors, so that chemistry can be easy and fun for one and all. See you in the next video.